Here we are in Unit 2. With Objective 1, we're just continuing to analyze piecewise functions. In this first example, it looks like we have what might be a 3-piece function, maybe a 4-piece function right here. We have a constant right here. We have a quadratic right here. We have a linear part right here. And then we have another quadratic part right here. Problem number 1, question number 1 says, state the open intervals on which the function is increasing. Well, we've got a couple of places where it's increasing, from here to here and from here to here. When the problem says state the open intervals, all they want to know is the domain, the x values. So it begins increasing at -4. And that part stops at -3. So we write it like this, -4, -3. But there's another part where it increases, and that is from x equals -1 to x equals 0. So we put -1, 0. Question 2, state the open intervals where it's decreasing. Well, we got a couple parts where it's decreasing. It's decreasing in this section right here, and it's decreasing in that section right there. So this section begins at -3, and it ends at x equals -1. And then this section begins at 0. And there really is no ending value of x because it continues to decrease forever. State the open intervals on which the function is a constant. Well, this is the constant right here, and it goes to the left forever and ever, so it's -infinity is where that constant begins, and it ends at -4. Now, the domain and range. Well, the domain, the values of x that the entire graph uses, it goes forever and ever to the left, and even though it goes down forever and ever, it also goes out forever and ever. So the domain is simply -infinity to +infinity. Now the range, the values of y, this goes down forever and ever, so it really doesn't have a low point, -infinity. It does have a high point right up here, and that is a y value of 6. And since that's a closed point, we close the bracket. Example number 2 is very similar to example number 1, except we add a couple of extra questions down here on question 5 and question 6. So again, we see another piecewise function. It's got a lot of parts. It has what looks like is a linear part, and then a constant, and then an absolute value part, and then a quadratic part, and then back to a linear part. Now the nice thing about this is we don't expect you to write the equations of this. All we have to do is analyze it. So problem number 1, where is the function increasing? On what open intervals is the function increasing? Well, here's an increasing part right here from x equals -1 to x equals +1. So -1 to +1. But there's another increasing part right here, this tiny little linear part right here, from +6 to +7. Where is it decreasing? Here's a decreasing part. Now here's a decreasing part that appears to be either linear or absolute value, but then it continues to be a decreasing part, but it changes shape. It's quadratic. Some students like to write this as 2 decreasing parts, but it's really only one. Let's take care of this one first. It begins at -infinity, and then it stops decreasing at an x value of -3. Now, this part, let's just write it as one long decreasing part. So it begins at 1 and it ends at x equals 6. Where is the open interval where it's constant? Well, right here. It begins with an x value of -3, and it ends at an x value of -1. State the domain and the range. The domain, all the values of x that are used in the entire graph. Well, it begins at -infinity, because not only does this go up forever, but it goes out forever as well. But it ends right here, and that's with an x value of 7. Now the range, the lowest point on the graph is at a y value of -4. And the highest point on the graph, this goes up forever and ever, so there really is no highest point on the graph. It's at infinity. Now, problems 5 and 6, or questions 5 and 6, are a little bit new. What are the coordinates of relative minimums and relative maximums on this graph? In order to be a relative minimum, the graph has to come down, and then it immediately has to turn around and go back up. So this is not a relative minimum because it flattens out. And this isn't a relative minimum because it flattens and then it goes back up. Here's your relative minimum. Here's your one and only relative minimum on this graph. And that's at 6, -4. It comes down and then it immediately turns around and goes back up. Identify the coordinates of any relative max. Well, in order to be a relative max, it has to do the opposite. It has to form a peak. It has to work its way up and then immediately turn around and go back down. So that's what that point does right there at 1, 5. The third and final example for objective 1, another piecewise function. It's in 3 parts. We're going to analyze the same things we've analyzed before, but we're also going to add the last problem, problem number 5, that we're actually going to write the 3 pieces of the function. So, first of all, problem number 1, the open interval where f is increasing. Here's an increasing part right here, and there are no other increasing parts. So from -4 to -2. The open interval where the graph is decreasing. Here's a decreasing part right here, and here's another decreasing part right here. So there are 2 places where it's decreasing, from an x value of -infinity all the way over on the left, to an x value of -4. And then this part right here that starts at an x value of 2 and it finishes at an x value of 6. State the domain and the range. Well, not only does this go up forever and ever, but it goes out forever and ever. So our domain begins at -infinity, and it works all the way through to an x value of 6. And since that's a closed point, we actually get to use 6. Now, the range. The range, the lowest value is -1. And it is -1. We do get to use -1. And the highest value, this side of the graph, goes up and up and up forever. So there's our right-hand side of the range. Now, the domain, and this is the range. Relative maximums and minimums. If I'm looking for a relative max, remember a relative maximum has to be a peak. The graph has to work its way up and then immediately turn around and go back down. Well, if you look on here, there is no place where there's a relative max. This part works its way up, but it doesn't immediately go back down. It flattens out. So there is no relative max on this graph. Now, relative min. On the other hand, relative minimums have to work their way down and then immediately turn around and go back up. So there is a relative minimum at right here at -4, +1. Now we're going to come to the new part of the objective where we actually write each part of the function. Now going back and reviewing it, this is a quadratic part, so this is a parabola, this is a constant, and this is a linear with a decreasing graph with a negative slope. So that's what my three pieces have to look like. Don't try to do them all at once. It's overwhelming. Take each one of them one at a time. Let's take the quadratic part first, the parabola. The most important point on a parabola is its vertex, right there, which is at -1, -2, -3, -4, +1. Well, in order to have a vertex at -4, +1, the equation has to be very specific. It has to be x plus 4 squared plus 1. Remember, opposite, same. So in order for the vertex to be -4, +1, the equation has to look like this. But the parabola is restricted. Actually, on the left-hand side, it isn't. The left-hand side of the parabola goes up forever and ever and ever. But the right-hand side of the parabola ends at x equals -2. This is where the graph changes shape. So we say that the restricted domain is -infinity is less than x, which is less than or equal to -2 for the quadratic part of this graph. Now, let's move on to the constant. The constant would be y equals 5, or f of x equals 5. But that's only for x values from -2 to +2. Now, we've already got -2 included in this one, so we can't include it in the other one too. So -2 is less than x, which is less than or equal to +2. Now, the last part of the graph is this linear part that has a negative slope. Well, we can figure out what the slope is really easily. 1, 2, 3, 1, 2. -3/2. Down 3 over 2. Now, I'm going to pick this point to use to write the equation, but I'm also going to show you you could have used this one and that one. Well, this point is 2, 5. Well, in order for that point to be on the line, it has to be x minus 2 plus 5. And that would be for all values of x that are between 2 and 6. Now, just to clean it up a little bit, we like to do this. F of x equals, and we do this, and we do this. But that's it. Now remember, I told you that there are a couple of other equations that this linear part could be if we used the other 2 points. So let's use this point instead. +4, +2. That would be -3/2. The slope hasn't changed, but x minus 4 plus 2. Now, what if you wanted to use this point, which is 1, 2, 3, 4, 5, 6, -1? -3/2 x minus 6 minus 1. So I happen to use this equation that matches up to the first point of the linear section. You could have used this equation that matches up to the middle point, or you could have used this equation that matches up to that point. So and that is writing a piecewise function.